Hello and welcome back. In this video tutorial, we're going to be looking at solutions for physics homework number 7, constant acceleration. In this homework, we're going to be applying the following ideas. Let me go ahead and move this down because we're going to need the following equations and ideas in order to make this work. Number one, when you see the following variables, v naught, a, and t, you're going to use the equation v equals v naught plus a t. That is, I think, equation number 6 or 7 on our equation sheet. I'm not sure, but I believe it's one of those. Okay, so that's if you see that list. V naught, a, and t. Okay, now if you see x naught, v naught, a, and t, we would use the equation x equals x naught plus v naught times t plus 1/2 a t squared. Okay. If we have, let's say we have v naught, a, x, and x naught, we have those variables, then we'll use the equation v squared equals v naught squared plus 2 times a times the quantity x minus x naught. Okay, so we have these variables, we're going to use that equation. When we have these variables, we're going to use that equation. It's a matching game, guys. When we see these variables, we're going to use that equation. Okay, now finally, if I see x naught, v naught, and t, and I don't see a, well, then I'm going to use the equation delta x equals v plus v naught over 2 times t. All right, so if I'm given this list right here, I'm going to use this equation right here. Now, according to our formula sheet, this was equation number 8, this was equation number 9, this was equation number 10, this was equation number 11. So when I call for them, I'm going to refer to them by number. So, hey, we're going to use equation number 9. We're going to use equation number 8 right here. So have your formula sheet available and right next to you as you do this particular practice. One thing to note about displacement here, recall displacement is the change in position, final position minus initial position. Well, 99.9% of the time, the initial position usually equals 0, which means you can really say that this is either x or delta x equals. So you could put it as both. Delta x or x, right? You could write it either way. Okay. Another thing to consider as well, when we're talking about free fall, this is vertical acceleration specifically. Okay, free fall acceleration due to gravity. Now, what that means is an object is either going to slow down when it's going upwards or speed up when it's going downwards because of gravity's downward pull. Gravity always pulls towards the center of the earth. So objects that are thrown upwards are going to slow down. Objects that are dropped or thrown downwards are going to speed up because of this downward pull of gravity. Now, gravity itself is a negative force, and it's going to involve essentially negative acceleration on an object. Now, the value, the acceleration due to gravity, is going to be written as little g. This is the acceleration due to the force of gravity. And the value for little g that we're going to put in is 9.8 meters per second squared, right? Or we can do is we can just say in place of acceleration, we'll put negative 9.8 meters per second squared. Okay, so keep that in mind when we do our problem solving. For free fall acceleration, right, we need to make sure that A is a negative 9.8. Let's begin. Number one, a car is at rest on a horizontal surface. The accelerator is applied and the car accelerates at 3 meters per second squared. What is the speed of this car after 6.5 seconds? What will be the average speed during these 6.5 seconds, and how far will it move during these 6.5 seconds? Well, we generally want to try and develop a common list for every constant acceleration problem. So this is a constant acceleration problem, okay? And I know this, okay? I'm gonna write the concept over here. I know this a couple reasons. One, it's telling us the word accelerates. It's giving us the unit of acceleration, and it's telling you the car starts from rest and gains speed, right? So since there's a change in speed, it's an acceleration problem. Be prepared to make this list for every acceleration problem. X, x naught, v, v naught, a, and t. Now, a car at rest would start with 0 initial velocity, so you put that in there. We're given the acceleration, so that's 3 meters per second squared. We're assuming the car starts from a 0 position initially, unless the problem states otherwise. Well, what does this mean? What will be the speed after 6.5 seconds? So 6.5 seconds is the time. V is the question mark for part A, and X, how far, is the question mark for part C. Okay, so that's our list right here. Let's go ahead and begin. If we're going to look at part A, what will be the speed of the car after 6.5 seconds? We're looking for this. Keep in mind you have these given to you. Well, that to me, if we play matching game here, that to me looks like that list right there. So we're going to use equation number 8. Okay, so for part A, equation number 8 says V equals V naught plus AT. Now, anytime you can cancel a variable, do it. So I can cancel V naught this way, and now I'm basically plugging into A times T. Okay, so A, you can see, was 3. Now, normally I'm not going to write the units in the substitution, but I'm going to do it this once just to kind of show you how the units cancel correctly. And then T was 6.5 seconds. You'll notice, ladies and gentlemen, this seconds cancels with one of these, leaving you with a unit of meters per second, which is the unit of velocity. So V, when we multiply those two, we'll get about 19.5 meters per second. Part B, we're looking for the average speed during this time interval. Well, there's two ways we can calculate average speed. It's displacement over the time interval, but we don't have the displacement, so that's not going to work. The other way we can take the average of any two values is to take the final value and the initial value, add them up, and divide it by 2. That's another way of finding the average during a particular time interval. So this would be 19.5 plus 0 divided by 2. in which case you would get about 9.75 meters per second squared. Okay, and finally, in part C, we're looking for the displacement, how far it went. So if I'm looking at how far it went, I could use equation number 11, because that has how far it went. I could use equation number 9, because that has how far it went. And I could also use equation number 10, because that has how far it went too. But I would probably not choose to use equation 10, only because I'd have to solve for it. Let's use equation number 11. It's nice and simple. X equals v plus v naught over 2 times t. Okay, we're going to plug into that. I'm not going to plug in units this time. So we have 19.5 plus 0 divided by 6.5. So go ahead and take half of that, multiply it by 6.5, and we get that this object, this car, moved 63.4 meters. Number 2. Suppose that another car is moving with a speed of 18.5 meters per second when the brakes are applied, so as to slow the car down at a rate of negative 2.85 meters per second squared. All right, let's see how we approach this one. So remember, the first time we read this, let me just move this on down here. The first time we read this, we want to make sure we're reading for concept. Now, I can see that this is a constant acceleration problem because, well, number one, I'm given acceleration here because of that funky unit of meters per second squared, I know. But then I also know that it says the word slowing down, right? And I have different speeds. I start with this speed, and I'm asking to find another speed. So the fact all of that information alone tells me this is a constant acceleration problem. What do we do? As soon as we identify a constant acceleration problem, you immediately list the same 6 variables. Let's do that. X, x naught, v, v naught, a, and t. Okay, now you read it one more time, but now you begin to annotate. So suppose that another car is moving with a speed of 18.5 meters per second. Well, that's the first speed listed in the problem, so that has to be v naught. So v naught is 18.5 meters per second. When the brakes applied so as to slow the car down at a rate of negative 0.2.85 meters per second squared. Well, the meters per second squared is the dead giveaway. This is acceleration. Negative 2.85 negative 2.85 meters per second squared. Okay, we have that. Now we start to read part A, B, C, and D one at a time, and we're going to figure out what some of the other things are. So part A, what will be the speed? That means we're looking for V. Part A, we're looking for V at 3.55 seconds. Okay, so for this, we are looking at a time of 3.55 seconds. Now, please understand, if the conditions in the problem ever change, then you have to reestablish a brand new list, okay? But for right now, while the conditions are the same, we're gonna keep the same list going to organize it, all right? So based on this, here's what I'm looking at. We're looking for V. We've got this, right? I'm thinking you should be able to use equation number 8 again at the top. V equals V naught plus AT. Okay, let's write the equation down. V equals V naught plus A times T. Now this time, you cannot cancel V naught because V naught has an actual value, okay? So we're just gonna go ahead and substitute. We're gonna go 18.5 plus negative 2.85 times 3.55. Now, it would be advised that you take care of this first and then go ahead and subtract 18.5 and then that product. So 18.5, let me see. Now, it's going to end up being minus because plus a minus is a negative, so minus, and then open parentheses, 2.85 times 3.55. Okay, and that gives us about 8.38 meters per second squared. Okay, let me just copy this down real quick. All right, part B, we are looking to find the displacement, how far it went. So how far it went, we can use our equation number 11. Okay, delta x equals v plus v naught over 2 times t. Which will be 8.38 plus 18.5 over 2, and then times t, which would be 3.55 seconds. So put that in your calculator. We're going to go 8.38 plus 18.5, hit equals, divided by 2. Then go ahead and multiply it by 3.55. 8.38 plus 18.5 divided by 2 times 3.55. That gives us 47. About 47.7 meters. Okay, part C, we're looking for, and it's kind of different conditions. Now it says how long, we're looking for time, will it take the car to stop? You've just reestablished new conditions because now the final is now 0. So for part C, we now need to reestablish a new list. So let's go back and let's write our list again. Okay, so we have x, x naught, v, x naught, v naught, a, and t. So x, we don't know what it is yet. I don't know how far, because this 47.7 was only for that time. So it's gonna go farther, right? And actually that's gonna be part D. Part D is what we're looking at, how far it went. Still assuming x naught is 0 when we start from, basically we're gonna start from 0 unless the problem tells us otherwise, okay? V, well, I don't know what V is. That's actually what we're looking for. No, it's not. I'm sorry. We are given V. V equals 0. V equals 0. The original speed was 18.5 meters per second. Same acceleration, mind you, same acceleration of negative 2.85 meters per second squared. Okay, and we're looking for how long. So based on this, right, I'm looking for time, but I've got those variables there. So again, it's going to end up being the same equation number 8. V equals V naught plus A times T. remember, to solve for t, you need to be able to get rid of v naught and a. Subtract v naught from both sides. We get v minus v naught equals a times t. Then go ahead and divide a both sides. Okay, and we get t equals v minus v naught over a. That's what we're plugging into. Okay, so t equals, v was 0 minus 18.5, okay, over a, which is negative 2.85 meters per second squared. So 18.5 divided by, the negatives will cancel, you see, 2.85, and we're looking at about 6.49 seconds. It's going to take about 6.49 seconds to come to a complete stop. Almost 6.5 seconds. Okay, now part D is asking you how far it's going to take this car before it comes to a stop. So it's using the same conditions, therefore we're going to use the same list. Okay, but now we know what the time is. The time is 6.49 seconds. So we have a bunch of ways we could go about doing this. Okay, part D, and I'm just going to kind of squeeze this on over here. I'll write it over here. So part D, okay, there's two ways we can go about getting that done, and I'll walk you through this two different ways, okay? If I use equation number 9, which is x equals x naught plus v naught t plus 1/2 at squared, it's not a bad idea because it's already solved for x. You just got to plug in. Now, x naught was 0, so v naught t plus 1/2 a times t squared. So v naught was 18.5 times time, 6.49. Okay, the acceleration, negative 2.85 meters per second squared, and again, 6.49 right there. So if you take this in chunks, if I do this part first, 18.5 times 6.49, right, we're getting about 120.065, plus a negative is a minus. So I'm going to start over here first, subtract that, so square it, 6.49 squared times 2.85, and then take half. 6.49 squared times 2.85, then take half. And we're looking at about 60.02, and x would be the difference there. So 120 minus the 60 would, of course, be 60. So it's going to go 60 meters. Now, there's another way to do it. There's another way to do it if you used equation number 11. So I'm going to say a big or we could have gone delta x, which if x naught is equal to 0, remember delta x is equal to x minus x naught, right? That's equal to 0. So that's also equal to the average velocity times time. Okay, now the final velocity is 0, so it's really the initial velocity times time. Initial velocity divided by 2 times time. So 18.5 times time, 6.49 seconds, right? And then divided by 2. So 18.49, sorry, 18.5, I'm mixing up the numbers here, times 6.49, divide that by 2, and what do you know? Coincidence? I think not. Okay, just multiple ways of doing the same thing. Number 3, suppose that the Space Shuttle Columbia accelerates at 14 meters per second squared for 8.5 minutes after takeoff. Part A, what will be the speed of the shuttle at the end of 8.5 minutes? Part B, how far would the shuttle have traveled during this time? Okay, so first of all, I know this is an acceleration problem because of that word and that value right there. So what I'm going to do there is I am going to make a constant acceleration list. Now, normally my acceleration list looks like this. Zoom in here. Normally it looks like x, x naught, v, v naught, a, and t. That's my normal list every time. Okay, but you have to understand, space shuttle takes off in which direction? Well, vertically, in the y direction. So I need to account for that, and I'm just going to do that by changing the x to a y. So this becomes y, and this becomes y naught. It's the only change I really need to make. Okay, now let's reread one more time. So suppose you have Space Shuttle Columbia accelerates at 14 meters per second squared. Well, we're given the acceleration there. For 8.5 minutes. Well, there's something wrong with that. You see, this unit of minutes and that unit of seconds, well, they don't match. You got to make them match. So here's how we're going to do that. We're going to set up a conversion factor such that, well, 1 minute, there are 60 seconds. We're converting minutes into seconds. So 8.50 times 60 would be 510 seconds. So keep that in mind. We're going to need to do that. All right, this part right here, what will be the speed at the end of 8.5? So we're looking for this. Now, we weren't given the initial speed, but we have to make a really gigantic assumption. Pretty sure the space shuttle started from rest, right, before the thrusters were engaged. So I think we can make a fair assumption that the whole thing starts from rest. Okay, now if the space shuttle starts here and takes off, we're gonna let y naught equal 0 on the ground, and we're gonna let y here equal the height to what it gets to. Okay, so y naught is 0, and I don't know how far it goes. Okay, but that's literally part B, and that's literally part A. So let's take a look at how to do this problem. Part A, I am trying to find the speed, right? And I'm given V naught, A, and T. So once again, equation number 8 will work well. V equals V naught plus A times T. Realize you get to cancel the V naught, and we'll go ahead and plug in for A times T. So A would be 14, T would be 510, and V would equal 510 times 14 is 7,140 meters per second. Okay, part B. Part B is looking for how far it went. So I'm going to jump right on, since I have a change in velocity and a time, I'm going to jump right on equation number 11. Now, instead of writing it delta x equals v plus v naught over 2 times t, I'm just going to rewrite this. Remember, delta x, when x naught equals 0, delta x is the same thing as x. But instead of writing x, I'm going to write y. Okay, that's how I'm going to find out how high it gets. Let's plug into it. Okay, V final is 7,140, right, plus 0, times a time of 510 seconds. So 7,140 plus 0 divided by 2 times 510. And we're looking at about 182.07. We're looking at 1.8, right? 20 times 10 to the 6. So 1.82 times 10 to the 6 meters, which if you move the decimal place 3 to the left, it would be 1,820 kilometers high, right? So that's another way we can think about it too. Right? Either of those would be fine. Number 4. A ball is dropped from the top of a building to the ground below. Assuming that the acceleration due to gravity is negative 9.8 meters per second squared, and that it takes 2.87 seconds for this ball to reach the ground. Part A, what will be the speed of this ball as it reaches the ground? Part B, what is the average speed of the ball as it falls to the ground? Part C, how tall is the building? Well, we're at about that time where when you're dealing with free fall acceleration due to gravity and projectile motion, it really helps to draw a sketch to sort out everything. So let's do that. Okay, so here's our building. Now, a couple things that I'm going to note about our building. I'm going to let y equal 0. Now, the ball is starting up here and it falls like this. I'm going to let y naught equal the height from which it was dropped. Okay, so that is the reference frame that I'm establishing in this problem. Now, I could have done it differently. I could have started from 0. Okay, all that means is that this would have to be a negative height, right? Because I'm dropping below 0. So I can establish my reference frame any way I want, but I have to be consistent with it too. Okay, now what is the acceleration due to gravity all about? Okay, now what that means is when an object drops, so see a falling object here, okay, when it's dropped, the initial velocity is equal to 0. The velocity at 1 second, meaning it's falling at a rate of 9.8 meters per second every second. So after 1 second, right, its speed would be about 9.8 meters per second, or its velocity would be negative 9.8 meters per second. Its velocity after 2 seconds would be another 19.8 or 19.6 meters per second. After 3 seconds, the velocity would be another 9.8. See how it's a consistent increase in velocity of 9.8 meters per second? That would be negative 27.4 meters per second. So that's what the acceleration due to gravity is all about. It means gravity accelerates a falling object or an object rising against gravity at a constant rate, which means you'll automatically just link A with 9.8. Okay, that'll be an automatic. All right, so I know this is a constant acceleration problem. Okay, constant acceleration problem. And as such, I need to make my list. Now, my list is going to look a little different this time. Since it's a dropped object going in the y direction, not the x direction, I'm going to list y and y naught instead of x and x naught. Still have v and v naught, still have a, still have t. Okay, my list stays consistent. Okay, now a ball is dropped. That is code for v naught equals 0. When a ball is dropped, it has no initial speed. Okay, we know A is equal to negative 9.8 meters per second squared. All right, and we know that the time is 2.87 seconds. So we know all that. So what will be the speed as it reaches the ground? That's part A. Okay, what is the average speed? We're looking for V bar. How tall is the building? Well, that would be y naught. You're looking for part C. Remember, we're letting y equals 0 at the bottom. Okay, so how are we going to approach part A? Well, part A, I'm looking for the speed as a function of time. V naught is 0, A is negative 9.8, and T is 2.87. So I'll use my equation number 8 again, V equals V naught plus AT, right? But we're solving it for speed, okay? Recall that V naught was equal to 0 because it was dropped. And so we're plugging into A times T. Okay, A is negative 9.8. T is equal to 2.87 seconds. Multiply those two. And we get about 28.1 meters per second. Now, the reason I didn't put the negative in there, so the velocity would be negative 28.7 because it's a downward velocity. The ball's dropping, okay? But the question said, what is the speed? So the speed is the absolute value of the velocity, meaning just 28 meters per second. So I'm just going based upon how the question was formed. If the question was asking for velocity, my answer would have been negative. Part B, well, average velocity, we worked that out last time, is just the initial plus the final divided by 2. The initial, the final would be 28.1 plus the initial is 0. Okay, divide that by 2 and you get about 14.1 meters per second. Part C is looking for how tall the building is. So now you're looking for why not. Okay, look for why not. So a couple things I know. So if I'm looking for how tall the building is, keep in mind that if I put this in here, delta y equals v plus v naught over 2 times t. Please understand that this would be y minus y naught, right, equals v plus v naught over 2 times t, and y is 0, right? So what are we kind of looking at here? Well, y is 0, but you have to remember v naught is also 0, and v is a negative value, right? So the negative here and the negative here will end up canceling. So I don't really have to worry so much about negatives. And why not? Well, that's the height. That's what I'm looking for. So the height that it's dropped from is going to be v, the speed, divided by 2 times the time. That's what I'm plugging into. Okay, v is 28.1. The time was 2.87 seconds. And if we plug 14.1 times 2.87 seconds, we find that the ball falls a total distance of 40.5 meters. But you got to realize the distance it falls is the same as the height of the building. Therefore, the building had to have been 40.5 meters tall. Number 5. A ball is thrown straight upward with an initial speed of 52 meters per second. Okay, that's all we're given. But you got to remember, there's some other things that are implicit in what you have. So first of all, again, with free fall acceleration due to gravity, if I have a ball thrown upwards, gravity is going to pull down on it and make it slow down as it's going upward. So just draw a little sketch. Okay, ball's going upward. Now, there's 2 parts to this problem. You can see part A is looking for the speed at the highest point. Part B is looking for the speed when it returns to the ground. Part C is looking about how long it takes to reach the highest point. And then part D is, the how high it actually gets. All right, so what we're going to do is we need to create a reference frame. So reference frame is all about a starting point. Where's the origin of the problem, and what direction is positive, okay? And also, how are you going to measure time within that reference frame? But mainly it's an origin, starting point, and which direction is considered positive. If you have that, then anything moving in that reference frame needs to all be consistent. So I'll go ahead and start with y naught down here being 0, and y at the top being the height that the ball gets to. Okay, so that's the choice of the reference frame I'm going to make. Now, this is a constant acceleration problem. We know that because the ball's going to change speeds, right? Gravity's going to slow it down. So let's go ahead and make our standard list. Okay, remember, instead of x, we would have y not. We would have v naught, a, and t. Okay, well, a we already know. See, it's not explicitly stated, but A we should already know. If the ball is slowing down because of gravity, that means A is the acceleration due to gravity, which is a constant negative 9.8 meters per second squared. So let's go and write down that first. Remember, we established the bottom as the initial position, so y naught is 0, okay? And you also know that the initial velocity going upwards is 52 meters per second. So those are the things we know so far going into this problem. Part A, what is the speed of the ball when it reaches the highest point? So part A is more of a conceptual thing. What's the ball going to do as it goes upward? It's going to slow down. What's it going to do at the highest point? It's going to stop, right? So the velocity at the top should be 0. Okay, there we go. Sorry about that. I like to have my stuff organized. Now, part B is asking you what will be the speed of the ball when it returns to the ground. Well, if the time it takes a ball to go up is symmetrical with the time it takes to go down, that means the speed at any point going up is symmetrical to the same speed at that same level coming down. So the velocity when it comes back to the ground, we'll call it v ground. Now, it's now, keep in mind, it's not the velocity after it hits the ground. That would obviously be 0. It's the velocity right before hitting the ground. Well, that would just be the opposite, right, of this, right? It would be negative 52 meters per second. Okay, so we have that, but keep in mind something here, guys. That's the velocity. The question's looking for the speed. So the speed is just the absolute value of the velocity, and so I would write just the 52. So it's 52 going up, it's 52 at the same level on its way back down. Okay, so A and B were really more conceptual questions rather than ones we calculate. All right, now we can get into some calculations. Part C, well, we're looking for how long. How long does it take to get to the top? That's the first question mark. Okay, part D, how high? Well, that's y, right? That's the height. Okay, then we can start focusing on speed as a function of very specific times. Okay, so we can get into that later, but let's find how high it takes to get to that highest point and how high that highest point actually is. So here's what I'm looking at. I'm looking at the fact that at the highest point, the velocity is 0, so I know that. I know those, and I'm looking for time, okay? That tells me equation 8, right, is pretty suitable for this. Okay, now we got to solve this equation for time. So remember what you have to do. We're going to cancel the v because velocity is 0 at the top. So we get 0 equals v naught plus a t. In order to get t by itself, you have to get rid of the v naught and the a. So we'll start by subtracting v naught both sides. You get negative v naught equals a times t. Okay, then to get t by itself, you're going to divide both sides by a. Okay, so that's what's going on with this problem so far. Plug in. Okay, we have negative v naught over a. Which is going to be negative 52, right, meters per second, over a, which is negative 9.8 meters per second. Okay, and when you divide negative 52 by negative 8, you get negative as a positive, and so 52 over 9.8 is about 5.31 seconds. So it takes a little over 5.3 seconds to get to the highest point. Okay, letter D. We're looking for how high it is. Now I'm looking for using an equation that is essentially height as a function of time. And there's two of them, so I'm gonna show you both ways, and as you guys work this, you choose what seems to work best. I could use equation number 9, which says x equals, but remember, instead of x, I'm writing y. So y equals y naught plus v naught t, right, plus 1/2 at squared. And I would do the following. I would make that equal to 0, and then start plugging in because it's already solved for y. So v naught times t plus 1/2 times a times t squared. So it's 52 times 5.31, right? And then plus 1/2 times negative 9.8 times 5.31 squared. Okay, now if I kind of compute this, 52 times 5.31 is about 276.12, plus a negative is minus, and if we go 5.31 squared times 9.8 and then take half of it, we're looking at about 13.16, and if we end up subtracting those, you'll get about 138 meters is how high the ball gets. Okay, now keep in mind, right, there's always another way. So I could go, remember, delta y is the same thing as y in this case because y naught is 0. V plus v naught over 2 times t. Okay, plugging into that, what do we have? We have v, which is 0 at the top, plus v naught, which is 52. 52 divided by 2, right, is 26, times the 5.31 seconds that it takes to get to the highest point. And what do you know? You get 138 meters. So you have options, ladies and gentlemen, you have options. And well, you don't always have options, but when you have enough variables present, you start to have more options. And that's, as you get better at this, you're gonna start to kind of pick at what the options are gonna work best for you. All right, now for part E, we're looking for the speed as a function of time. Well, that automatically is going to be equation number 8 again, but this time we're not gonna cross that out as 0 because now you're looking for the speed at some point on the way up. So just plug in. We're gonna go 52, that's v naught, plus a times t. Now keep in mind what a is, negative 9.8, right? And t is 5.31. Okay, so that would be the same as 52 minus, what, 37.73, and you should get about 14.3 meters per second. Make sure you're putting this in your calculator yourself, right? Prove to yourself that you can get this right independently, okay? And then finally, we're looking at the average speed, right, of the ball during this same period. So the average speed, well, just take the average of two numbers, v plus v naught over 2. Okay, so v would be what? 14.3, that's how fast you're going, plus the initial speed, 52, okay? And then take half of that. Okay, put that in your calculator. 14.3 plus 52 equals, just divide that by 2, should get about 33.2 meters per second. Number 6. You're standing at the top of a building 135 meters tall. You throw a ball upward with a velocity of 22 meters per second. At the exact same moment, a friend throws a second ball upward from the ground with a velocity of 46 meters per second. These two balls then collide at some time later. Part A, how long after the two balls are released will they collide? Part B, what will these two balls, where will these two balls be when they collide? C, what will be the velocity of each ball when they collide? And D, what is the relative velocity of the balls at the moment they collide? Okay, now we really need a picture to sort this one out. Okay, so I'm going to draw my building. Okay, so here's you. Throw a ball. It's going to go up and then down again, right? Then there's your friend. Throws a ball up, right? They're gonna collide somewhere. Now, they're not gonna collide exactly the way I drew it in the picture, but they're gonna collide somewhere between the top ball falling down and the bottom ball going up, most likely, okay? So the first thing we need to do is, again, establish a reference frame. But here's what we're going to do. We're going to establish the reference frame with regards to each person. So we're going to call you person 1 and the other one person 2. Okay, what I mean by that is if I'm going to establish the ground as 0, then I'm going to call this y naught 2 equals 0. Whereas this person here, y naught 1, right, would be 135, okay, from where they're throwing it. So keep that in mind. V naught 1 would be 22 meters per second, and V naught 2 down here would be 46 meters per second. So I'm just establishing very specific subscripts for very specific people when we have two objects moving in the same reference frame. All right, so now something to consider. It says, how long after these two balls are released will they collide? Well, think about it. They're going to collide when their times are the same and when their positions are the same. So first, let's come up with a function that's position versus time. How about equation number 9? Y equals y naught plus v naught t plus 1/2 a t squared. Now, we would just write this kind of like this. Y1 would equal y naught 1 plus v naught 1 t1 plus 1/2 a1 t1 squared. So I'm just giving a 1 subscript to everything, right? And then same thing here. Y2 hold off on Y2 real quick. With Y1, okay, that's the top person. Keep in mind, the initial position will end up being 135. Okay, we're going to plug in 22, right, for this. We're going to plug in 22 for V naught 1, okay, and we don't know what that is, okay? So in other words, this is going to end up being Y1 equals 135 plus 22 T1 plus 1/2 A1 T1 squared, okay? Now, for the second object, ball 2 down the bottom, it's going to be Y2, right, equals Y naught 2, why not, because we can, V naught 2 times T2 plus 1/2 A2 T2 squared. Okay, so now if you look at this one, Y naught 2 was 0, remember? And V naught 2, we're going to substitute 46. Okay, so, and again, I don't know what Y2 is. But here's what I do know. When the ball collides, this will be the same as this. Those numbers will be the same. And if they're the same, then I get to set these equations equal to each other. Remember, this is transitive property of equality. If these y's are the same, then these two expressions are the same, okay? So here's what I would write. I would write 135 plus 22 t. Now I don't have to write t1 and t2 anymore because they will collide at the same time, right? Equals, well, what's left over? 0 plus 46t. So the equation is very, very simplified. And you're solving the equation for time. So let's go ahead and bring a 22t over here. And we have 135 minus 24t. Right? And we can see here the time, 135 over 24 puts it at about 5.63 seconds. So it's going to take 5.63 seconds for those balls to end up colliding. Okay, now in part B, okay, it's saying where will they collide? Well, you have two positions as a function of time, so pick one, doesn't matter. I'll pick the bottom one because I got to zero something out. So y2 equals 46t plus 1/2 at squared, and just plug into it. So 46, plug in the 5.63, plug in your negative 9.8 for A. Don't forget to square your t again. And let's compute. 46 times our 5.63 would be about 258.98. Okay, remember plus and negative is a minus. All right, when we square the 5.63 times 9.8, take half, is about 155.3. We'll go ahead and subtract those. And we find that the balls will collide at about 104 meters off the ground. Okay, now part C is asking for what the velocity of each of these balls just as they collide. So now we're looking at velocity as a function of time. So for that, we'll use equation number 8. V equals V naught plus A times T. Okay, but you gotta do it for each one. So V1, V naught 1, A1, T1, all that, okay? And then same thing for the other ball. So we're making this calculation happen twice. Okay, so V naught 1 would be V naught 1 is 22. So 22 plus, okay, and then V naught 2 is 46. Okay, go ahead and plug in. Remember, this happens at 5.63 seconds off the ground. Okay, and we find we get about, let's see, the velocity for the first ball is going to be negative 33.2 meters per second. That means it's going to be on its way down. And the velocity for the second ball is going to be about 9.17, okay, negative 9.17, meaning that one's also going to be on its way down. Okay, but they'll catch up with each other and they'll hit. Okay, now finally for part D, we're looking at the relative velocity between these balls. So the relative velocity is just going to be, instead of the velocity with respect to the Earth, it's the velocity with respect to each other. So just go ahead and take the difference. Which is about 24 meters per second.